Okay, for the last one is the goodness of fit, but for a normal distribution. Okay, so we want to know if the data that we have follows a normal distribution. That's it. So in this case, remember that the normal distribution, we have two parameters: the mean, the mu, and the mean and the standard deviation. So in this case, we will have two parameters to estimate, and so we are going to have a chi-square. This is alpha, and how many degrees of freedom is k minus 1, where k is the number of categories, k minus 1 minus the number of the parameters of the population that we are estimating. Every time that we estimate one population parameter, the chi-square loses 1 degree of freedom. So in this case, we would have k minus 3 degrees of freedom, because it's k minus 1 minus the two parameters that we are going to estimate. And again, this is going to be exactly the same. We are going to have the summation of the frequency minus expected squared divided by expected. And again, the expected number of elements that you have in each category should be at least 5. So cannot be less than 5. And the rest is pretty straightforward. So let's do an example. Let's do a problem. Let's do problem number 24. But, 24. Okay, what they gave us is actually the data. Okay, so problem 24, it says the weekly demand for a product is believed to be normally distributed. Use a goodness of fit test and the following data to test this assumption. Use alpha is equal to 0.1, okay, and the sample mean is 24.6. 0.5, I'm sorry, 24.5, and the sample standard deviation is equal to 3. Okay, so and they gave us the whole data over here. There's 30 numbers that this has 1, 2, 3, 4, 5, 6. So we have a n equal to 30. Okay, we have they already calculate for us the mean and the sample standard deviation. If they don't give us that information, we have to calculate it based on the data that they provided. Okay, now okay, first of all, we have 30 elements in the data, and we need to have at least 5 elements in each one of the categories in the expected value. So we are going to have how many categories? 6 categories. 30 divided by 5 is equal to 6, because we need to have at least 5 elements in each one of the categories. So we're going to have 6 categories. So we are going to divide my population or my distribution in 6 categories. Okay, this is the mean, this is 0, and this is Z. Okay, so we are going to divide each one, the distribution into 6 parts, because we need to have at least 5 in each one of the expected values. Now, okay, if we divide this, it means that each one of these elements is 100 divided by 6, or 1 divided by 6. 1 divided by 6 is equal to 0.1666. So each one of these elements has 0.1666, 0.1666, 0.1666, 0.1666, and 0.1666. A total is 1. Okay, because we have 6 categories, and each one of the categories, the probability is 0.1666. Now, what is this number over here? In order to find out what are these numbers, we need to go back to the standard normal distribution table and look for 0.1666 in the side and 0.16, or the closest, if you will, is hold on, 0.1666. The closest is negative 0.97. Negative 0.97 is the closest to 0.1666 because this is 0.1660. That's the closest. So we have the negative 0.97, and since this is a symmetrical distribution, and this is half and this is half, this is the positive 0.97. Okay, now this part over here is what? Is 0.332. This one over here, 0.332. That is, the closest is 0.43. Let's say this is negative 0.43, this is positive 0.43. And so we have this distribution over here, and we know that this distribution is the way it is. I mean, this is the standard normal distribution, and these are the numbers that follow these particular categories. Now, we are going to estimate, and that is why we are estimating. The mean is equal to 20.45, and the standard deviation is equal to 3. So we are estimating the mean of this distribution being the mean of the sample, and the standard deviation of the population is going to be estimated based on the standard deviation of the sample. Okay, so what are these numbers in here? Let me try to do it exactly. So what is this negative 0.97 in here where we have the 24.5 as the mean, and sigma is equal to 3. Okay? In order to do that, we know that z is equal to x minus mu divided by sigma, right? So we want to know what is this x. This is x. This is z. So it's z times alpha plus mu. That is how we calculate this value on this particular distribution. This is a standard normal distribution, and this is a normal distribution with mean equal to 24.5 and sigma equal to 3. And this is the standard normal distribution with mean equal to 0 and sigma equal to 1. So what is this negative 0.97? Okay, negative 0.97 times the sigma 3 plus the mean 24.5, and this is 21.59. Okay, what is this negative 0.43? Exactly the same thing. 0.43 negative plus 3, that is the sigma, plus the 24.5, that is the mean, is the 23.21. what is this positive 43? Okay, this positive 43 times 3 plus 24.5, and this is 25, this number is 25.79, and the last number, this 0.97 over here, is times 3 plus 24.5, this is 27.41. Okay, so we have these 6 categories. Okay, which one is the category from 0 to 21.59? Okay, so this category over here. The next category is from 21.59 until 23.21. The next one is this one, is from 23.21 until 24.5. The next is 24.5 until 25.79, 25.79 to 27.41, and more than 27.41. Okay, we have the expected number in each one of the categories is what? 5. Remember that we have that situation, that's why we divide it in 6, because we need to have the expected number equal to 5 in each one of the categories. So, and what is the observed value, or this is the observed value? In this case, what you need to do is to observe your data. How many are between 0 and 21.59? Go to the problem. It's I lost it. Okay, go to it's on page 496. How many are between 0 and 21.59? Okay, the first one is 18. 18 counts up to 21. 18 counts. What else? In the following column, the 20 counts. In the following column, the 20 and the 19 counts. Okay, and the following number, the 21 counts. So we do have 5 numbers that are in the category. Okay, the second one between 22 and 23, let's say, 22 and 23. In the first one, we have nothing. In the second column, we have the 22 and 23, okay? The following column, we have the 22. The following column, we don't have any. The following column, we have the 22. So we have how many? 4 observed between 21.59 and 23.21, and so on. We need to count how many are in each one of the categories. We have 5, 4, we have 3 over here, we have 7 here, 7 here, and 4 here. If you add this, has to be the 30 that we have. If you do not end up with 30, then you miss one of the numbers, but it's pretty easy to go back and check the range of the observed values, and the observed values are the one that the book is giving you. And that's it. That's it. We have the observed, or the frequencies, we have the expected, and we need to compare these with a chi-square. This is alpha, and my alpha is equal to 0.1. How many degrees of freedom? Okay. How many categories we have? 1, 2, 3, 4, 5, and 6. 6 categories. So it's 6 minus what? Minus 1 minus 2. 6 minus 3 is equal to 3. So the degrees of freedom in this case is 3. And go to the chi-square, which I already lose it. Oh no, I have it. Chi-square with 3 degrees of freedom and 0.1. is 6.251. Okay, this is my critical value. And the test is going to be what? All for each one of the categories. The observed minus the expected, the square divided by the expected. So that my test value for the first one is 5 minus 5 squared divided by 5 plus the next 4 minus 5 squared divided by 5 plus so and so and so. This is 5 minus 5 is 0. 4 minus 5 is negative 1. Square is 1 divided by 4. Divided by 5, I'm sorry, this is expected, is 0.2. This is 2 squared, 4 divided by 5 is 0.8, 0.8, 0.8, and 0.2. If we add this frequency minus expected is squared divided by expectancy, if we add this element, that has to be equal to 2.8. And 2.8 in this case is over here, so we do not reject the null hypothesis. And again, the null hypothesis was what? It fits a normal distribution, and the alternative, it doesn't fit. Okay, so it fits. This data, the data that we have, really fits a normal distribution, or being more specific, we do not have evidence to say that these data do not follow a normal distribution. So we do not reject the null hypothesis. And that's it. Basically, that's all the chapter. It's very time consuming. It has to deal with a lot of calculation. Yes, it has to deal with many places that you can have some mistakes, but it really is pretty straightforward and that easy. It's pretty easy. So we have basically the chi-square distribution. Okay, it's an upper tail. This is alpha. How many degrees of freedom? It really depends. If we are dealing with the multinomial, where we don't have any parameter to estimate, it's k minus 1, where k is the number of categories. We have the Poisson. How many degrees of freedom? K minus 2. Why? Because we have to have this k minus 1 minus 1 parameter that we estimate. And the normal, how many degrees of freedom is k minus 3? It's the k minus 1 that we always have minus the 2 parameters that we need to estimate, the mean and the standard deviation, basically. And the test is equal to the summation of the frequencies minus what is expected squared divided by the expected. We add these numbers and we compare with this critical value. If it's in the rejection zone, we reject. What we reject, that it fits. And the alternative, it doesn't fit. Okay? So these are the hypotheses that we are testing. And it's always an upper tail test, so don't worry about that. And in the test of independence, it's pretty similar. We have a chi-square with how many degrees of freedom? N minus 1 times m minus 1. And that's it. The expected is, we calculate the expected having the total number on the column times the total number of the row divided by the total elements in my sample, and that is the expected. So we calculate that considering that the two variables are really independent from each other. So if the test is over here, we say the null hypothesis that, says that they are independent, and the alternative that they are dependent. And that's it, basically. This is chapter 12, and pretty easy.